Good morning, student. Today it is the second class of the topic work, energy and power. In the previous class we have seen, student, in which case the work is done, how the work becomes positive, how the work becomes negative. The formula for work done is, student, as we have seen, it is the dot product of force into displacement, student. Dot product of force into displacement, and it is given by Fs cos theta. Now, students, suppose there is an object of mass m. It is moving with certain velocity u. Due to the application of the force, student, the velocity becomes v after a time t seconds, student. Velocity becomes v due to the application of the force on this object, student. Now, student, the displacement during this time will be given by the third equation of motion, student, which we have studied. The displacement will be given by v square minus u square upon twice. Okay, student. Now, student, as you know, the work done in this case, the formula is force into displacement. Student, force is given by mass into acceleration, and displacement is this quantity, student. So if you see the expression of work done, student, it is coming out to be half mv square minus half mu square. It is a very important deduction, student, of the work done. Student, now see, if you see when is the work done. Work done means you have to apply force, and that force must causes displacement. Who can apply force, student? The agent who can apply force must have one physical entity known as energy. Energetic person can apply force. And that is why it is the capacity to do work is defined as energy, student. You have learned in the lower classes. Because an energetic person can only apply force, and he can make the work done by causing the displacement. By causing the displacement due to the application of the force, student. Now, student, see, here the work done comes out to be difference of two quantities, half mv square minus half mu square. Now, student, you see this expression. The work energy relation, just now I told you, capacity to do work. Capacity to do work is energy. This is energy, student. Okay. Now, friend, suppose this is one object is kept here, and I am just touching it. Now this is not moving, student. This is not moving. Now suppose this object is made in motion, and now it tracks. So this will start motion, student. First starting it was not moving, but now I brought this in motion. Now it will move, student. So what is this happening, student? This motion is creating the capacity to do work. Without motion it was unable to do work, student. As in case of hammer and nail, student. If I just place the hammer on the nail, nothing will happen. But when I bring the hammer in motion, that nail is pierced inside, means that there is a displacement on the nail, student. So due to this motion, student, that displacement is there. This means there is an energy due to the motion, and that energy, by virtue of motion, energy which comes, or the capacity of doing work which comes due to motion, student, energy due to virtue of motion is known as, student, kinetic energy. And that is why, student, you see in this term there is a velocity term is there, The basic term is, student, whenever there is an acceleration, it creates velocity. Acceleration creates velocity, student. And velocity means it is motion. So student, in this term there is a term velocity, and velocity means it is motion, and that is why this term has been given, named as kinetic energy, student. So have you understood, student, what is kinetic energy? The energy which comes by virtue of the motion. And just now I shown you the example. Motion, due to motion, it gains the capacity of doing the work. Without motion, it cannot do. So this energy which is coming by virtue of motion is kinetic energy, student, and that is why, student, here see the velocity, there is a change in velocity, student. It is v, and starting it was u. So this is, student, final kinetic energy, and this is initial kinetic energy, student. The difference of this is work done, and this is a very important theorem, student, known as work energy theorem. Work energy theorem, student. Which states that the change in kinetic energy is equal to work done. Now, student, if you see this expression, W work done is equal to half mv square minus half mu square, student. If student see, if u is greater than v, then this work done comes out to be negative. And if v is greater than u, work done comes out to be positive. Now here this meaning you have to understand, student. Now what happens is, student, when work is done on the object, work is done on any object, the energy of the object increases, student. Remember this. Energy of the object increases. And work is done by some person. The person who is doing the work, his energy will decrease, student. His energy will decrease. So, student, if we want to increase the energy of the system, you have to work, you have to do the work. This concept you have to remember. Work done will increase the energy, and work done by the person who is doing the work, that will decrease the energy. On that basis, the work is positive, and, student, work is positive and negative, student. So this is a very important concept. If you want to increase the energy of the system, we have to do work on that system. So this is means the main thing is you have to understand who is doing the work. The agent you have to consider. That it will clarify you whether the energy is increasing or decreasing. So how will you clarify? You see whether the work is positive or not, or whether the work is negative or not. This is how the is measured, student. Now, student, this is one more very important relation, student. Fs is equal to half mv square minus half mu square. See, student, how many quantities are related by this expression? 1, 2, 3, 4, 5. 5 quantities are related by this expression, student. It is a very useful expression for the numericals, student, also. It is known as work energy theorem, student. Now, student, there is another kind of energy which comes for example, student, this is a glass, and I kept a stone on the glass. Student, nothing happens as such. But, student, if I pick this stone up, so, student, while picking this stone up, I have to do work. As just now I told you, work will be done on the stone. work will be done on the stone. This will increase the energy of the stone, student. So what will happen, as soon as I leave this stone, it will come down and now this glass will break, student. This glass will break. Now see actually what happened when I picked up the stone from here to here. Two things has happened, student. First, work was done on this stone, so its energy has increased. And second thing, that energy which has stored in this, energy has been increased and stored. This you have to note, student. See, energy stored. First, energy increased and stored. If I keep it, nothing will happen now, because stored energy is there. Now if I leave it, that stored energy will be returned back in the form of kinetic energy, and this glass will break, student. So this is the another kind of energy, student, and how this has been achieved by changing the position. You see, position has been changed. Similarly, if I take the spring, student, see, this is spring, student. Now if I compress it, student, here say one ball is there. Now if I compress it and hold it, now if I keep this ball here, this spring will produce displacement in the ball in this direction. So here, student, what I have done, I have changed the configuration of the spring. Here I have changed the position of the stone. So student, due to change in the position, due to change in configuration, one more thing, work is done. When I am changing the configuration, I have done work. Work was done. So in this case, what happened was energy was stored, student. This energy, student, the name is potential energy, student. So now we have the second form of energy, student, which is stored in the object. Potential energy, student. So potential energy is energy due to change in position, configuration, or shape. And how the change was made, work done. This converts into stored energy, student. Converts into stored energy and known as potential energy, student. So one energy comes due to motion, that is the kinetic energy, and one energy comes due to change in the position, due to change in the configuration, due to change in the shape. But remember, student, work has to be done, then only this energy will come. Work was done means if no work is required to change the position, then this energy will not come, student. Remember this fact. So student, these two energy, kinetic energy potential energy, these two energy combined, they are known as mechanical energy, student. Mechanical energy, student. Now student, this mechanical energy is conserved. Mechanical energy is conserved. How? I'll take an example, student. When, student, I lift an object up, an object of mass m, Earth is pulling it downside mg, I am lifting it up in constant velocity, student. Constant velocity. So when I am lifting up, little bit I have to increase the force. Then only I can lift it up. Say I lifted it up to a height h and kept it here. So in this case, student, the work which was done by me is given by work done force into displacement mgh. This work done is known as, student, stored as potential energy. It is potential energy, student. Now suppose, student, this is the ground. I am throwing a ball with velocity u in the upward direction. Position 1. I have thrown it, student, with velocity u. Of ball of mass m. Now this ball will reach, it will decrease its velocity and finally it will return back, student. Say this height is h. This height is d, student. This is second position of the ball, this is third. Here the velocity is 0. This is the ground position, student. This is. So at the position 1, student, kinetic energy was half mv, mu square, and potential energy was 0, student, because it is on the ground. Height is not there. Just I have thrown it. Okay. So total energy at position 1, half mu square. Now, student, at position 2, this distance is d, student. Now, student, what is the velocity which is obtained on reaching this? I will apply the kinematics, student. Initial velocity u minus 2g, and this is displacement, student, d. This is the velocity which is. So the kinetic energy at the position 2 will be, student, half mv square. Now, student, what is the potential energy at this position? It is, student, mgd. Now, if I add, student, the total energy, if I add it, student, total energy again comes out to be half mu square. See, it is same as here at the position 2. Now, student, I will take the position 3. Here velocity is 0, student, the kinetic energy becomes 0. Potential energy, student, it will be mgh. Now, student, how much is this displacement, student, from this formula? This formula, student. I am applying the equation. Again the same formula, student. This is 0, u square minus 2gh. So h is, student, u square by 2g. So the potential energy comes out to be mg into u square by 2g. So again the total potential energy comes out to be half mu square, and total energy is again same, student. All everywhere we're getting half mu square, half mu square, half mu square, student. So, student, in this case what we have seen is that mechanical energy is conserved in this case. In this, and remember, in this case, student, the force acting was gravitational force. So this kind of force in which, student, the mechanical energy remains conserved, law of conservation of energy. This kind of force is known as conservative force. We'll come into later into detail into it, student. So this is the law of conservation of energy, student, proof of this, in which the mechanical energy is conserved. Everywhere the total energy is constant. It is same, student. Now, student, let's talk about the spring case. This is a spring, student. When when I am compressing this spring, there is a restoring force act, and that force is proportional to displacement, student. The spring force is proportional to displacement, and it acts in the opposite direction, student. If I apply force here, opposite to the displacement, it is act opposite to the displacement. If I apply this side, the force will along this side. If I elongate it, the force will be opposite. So the minus sign comes, student. So this expression becomes minus k. This k is known as, student, spring constant. So what is spring constant? F upon x. It is the force required to elongate the spring by unit length. Force required to elongate the spring by unit length. That is known as, student, spring constant. Now, student, in this case, as I started compressing this, the force is not constant, student. The force is not constant. See, this is the spring. Now suppose I compressed up to here. Force is acting. Now again I am compressing little more. This force has increased, student. This force is increasing. So it is a variable force, student. It is a variable force. So for variable force, we have designed a method, student, that first we will find small amount of work done for a small displacement, and then for total work done we will integrate, student. We will integrate. Now when integration, F is kx, student, kx dx. That minus sign is only for showing the direction, student. So I am integrating from, it will have a limit, student. This will give you total work done. So k is constant, student. K will come out, and integration formula, x square by 2 x2 x1. So work done will be k. Here I will place the limit, x2 square by 2 minus x1 square by 2. If I take this initial position to be 0, student, so work done will come out to be half k x square. This I have written x. This is the work done, student, total work done. And this work done becomes the stored energy, student. Stored energy, known as potential energy. So the potential energy of the spring, becomes, student, half kx. K is the spring constant, student. Remember again, student, in this case also the work is done. And that is why the potential energy is coming into play. Remember, student, the concept of potential energy will be based on the work done. The work must be done. That work done is stored as a energy, student. And this is how the potential energy comes. Now, student, work done, the basic formula which we have done till now is, say, F dot ds. And remember, if you remember the formula for velocity, it is ds by dt. So this now work done, another formula comes, student, F v dt. This formula is also very useful, student. In various numericals it has a use where it is very difficult to find out this S. So there you can find out work done by this formula, student. We will do some numericals also related to this in the next class, student. So student, today we have done work energy theorem and also we have proved law of conservation of energy, student. This you write down on your own words in your notebook. Thank you, student, for today's class.